Welcome to the One Source PH. In this video, you're going to learn about the atom. We're going to introduce some information about the atom starting with its history, some basic models that are proposed for the atom, and importantly, basic concepts about the atom. So way back even before Jesus Christ were born, there were philosophers that put forward notion about the atom. So one of them is Democritus, and he did this way back 460 BC. So he is a Greek philosopher, and he believed that the world, or suggested that the world was made up of two things, empty space and atomos. So this word atomos comes from the Latin word, or the Greek word rather, which is uncatable. Okay, and it has two main ideas. That is, the first one are atoms are the smallest possible particle of matter, and there are different types of atoms for each material. So the idea was abandoned, and it takes actually 2,000 years before a scientist in the person of John Dalton proposed again the atomic theory. That was back in 1804. So he said that all matter is made up of atoms, and atoms of one element are all the same. Atoms cannot be broken down into smaller parts, and compounds formed by combining of two or more atoms. And it says that Dalton's atomic model were like a billiard ball model, and he envisioned atoms as solid hard spheres like billiard or pool balls, so he used wooden balls to model them. So just like this. So this was proposed back in 1803. Research doesn't stop there because we do not know the dimension of the atom or if there are anything else that makes up the atom. So persons like or personalities of science like J.J. Thomson go ahead, went on and tried to discover more about the atom. So J.J. Thomson is the one responsible for discovering of the electron. So it was back in 1897 when he discovered the electron. So he was the first scientist to show that the atom was still made up of even smaller things. So a proof, the electron. So it is regarded as subatomic particles, but this is just the advent of the discovery, or this is just the start of the discovery of more subatomic particles. So electrons in 1897, the English physicist J.J. Thomson, who lived from 1856 to 1940, discovered the electron. Electrons are negatively charged subatomic particles. And Thomson, in order to discover the experiment, the electron have performed the experiments that involve passing electric currents through the gases at low pressures. He sealed the gases in a glass tube fitted at both ends with metal discs called electrodes. The electrodes are charged with the positive and negative, and the electrodes were connected to a source of electricity. So technically, there is a voltage difference that are developing on the nodes that causes the electrode to become positively charged, and the other is negatively charged. So this is how the setup goes. So we have the positive side, all right, and this is the positive side, which is called the anode, and we have the negative side, which we call the cathode, and this is connected into a high voltage source. And when he set this up, he noticed a green light, or a light that is emanating from one of the discs. All right, so he concluded that this is negative streams of particles, and he called it electrons later on. So the result of the experiment is a glowing beam of cathode ray that traveled from the cathode towards the anode. So the cathode ray, or we can call it electron beam, is deflected when several arrangement of charge plates were placed nearby. All right, so there is a deflection when a negative plate is moved, all right, towards the ray, and it is deflected towards the positive plate. Thomson found that the cathode ray is deflected by the electrically charged metal plates, and a positively charged plate attracts the cathode ray, while the negative charged plate repels. So according to J.J. Thomson, there is a need for the remodeling of the older version of the model, which is the billiard ball model of the atom. He called his model the plum pudding model, which is just like this. All right, so there is a spherical cloud of positively charged particle, and its electrons are embedded in it. So Thomson knew that the law of charges, which states that opposite charges attract and like charges repel. So he hypothesized that a cathode ray is a stream of tiny negatively charged particles, which is moving at a high speed. So at first he called it corpuscles, and later on he called it electrons. So these particles are also affected by magnets. So a cathode ray can also be deflected by magnet as seen in the diagram. Alright, so if you're gonna buy your own cathode ray, you can actually conduct the same experiment and prove for yourself that it is affected by electromagnetism. Some older versions of the TV or television sets, when placed magnet nearby, would actually create a certain distortion in the picture that is being produced in the picture tube of the TV. So that is a proof that this is affected by magnet. So J.J. Thomson went on and tried to describe the mass of the electron and the charge of the electron, but it was Robert A. Millikan, which is a U.S. physicist, born and lived from 1868 to 1953, who carried out the experiment and was able to find the quantity of the electron's charge. So he used the Robert Millikan oil drop experiment. So Millikan suspended negatively charged oil droplets between two charged plates. He then changed the voltage on the plates to see how this affects the droplets' rate of fall. So to his surprise, from his data, he found out that the charge on each oil droplet was a multiple of 1.6 times 10 to the negative 19 coulombs, meaning this must be the charge of the electron. Using the charge to mass ratio proposed by Thomson, Millikan was able to calculate the mass of the electron. Alright, so Millikan's values for the electron's charge and mass are similar to those that are accepted today. An electron has a unit of negative charge and its mass is around 1 all over 1,840 times the mass of the hydrogen atom. So meaning to say that the electron is 2,000 times less dense or less massive compared to the proton or compared to the hydrogen atom. The plum pudding model were short-lived or is short-lived. So because back those times when subatomic particles were discovered, scientists are wondering how the particles were put together in an atom, because they know that charges are interacting with one another and positive and negative charges tends to attract one another. So it will take no time for the electron to bump to the and crash, okay? So meaning to say that the model seems to be not reasonable. So scientists, or most of the scientists during those times, including J.J. Thomson, believed of his model and thought it like the electron were evenly distributed throughout an atom filled with positively charged material. In Thomson's atomic model, known as the plum pudding model, electrons were stuck into a lump of positive charge, similar to raisins stuck in a dough. So here are some physical properties of the electron before we move on to the next or latest discovery and revision about the model of the atom. So the electron is found to have mass, and it's about 9.1 times 10 to the negative 31 kilogram, and its charge is 1.6 times 10 to the negative 19 coulombs. Alright, so one of his students, in the person of Ernst Rutherford, were able to contribute in the understanding of the atom. Ernst Rutherford is from New Zealand, and he was born back in 1871 and lived until 1937. He was also awarded of the Nobel Prize for Chemistry in 1908, and you can see his picture on the New Zealand $100 bill. So let us try to check his accomplishments. So he was able to prove that the atom has a dense nucleus, and he called it the atomic nucleus of the atom. Rutherford's gold foil experiment were able to prove many things. So in 1911, Rutherford and his co-workers wanted to test the existing model, which is the plum pudding model of the atomic structure. So they devised the gold foil experiment. So their test used alpha particles, which are helium atoms that have lost their two electrons and have a double positive charge because of the two remaining protons. So in this experiment, the alpha particles are directed into the gold sheet, just like this. So a source is emitting alpha particles, and we can see that there is a detector or a film right here, and alpha particles that pass through the film would be detected at the back, but there are alpha particles that bounce back, and that gives rise to his question. So there must be something in the gold foil that is so massive that tends to knock off the alpha particles, which are massive and have a positive charge. So meaning to say there is a strong repulsive force, or there is a strong and massive matter that is hit by the alpha particles that makes it rebound. According to the prevailing theory, the alpha particles should have easily passed through the gold foil, but this doesn't happen, with only a slight deflection due to the positive charge thought to be spread out all over the gold atoms. But they have seen that some of the alpha particles bounce back. So they're trying to explain the scenario or the result of the experiment and try to create a new theory for the atom. So based on his experiment, Rutherford have made or have proposed and have concluded the following things or ideas. So the atom is mostly an empty space. There is a small dense center with a positive charge, and that is the nucleus. At this point in time, the neutron is not yet discovered. It will wait a few years, and it will be Chadwick and Goldstein who will discover the neutron. So, but at this point in time, Rutherford concluded that there is a small dense center with a positive charge. Rutherford discovered the nucleus in the atom. So he proposed the planetary model of the atom, wherein there is the center of the atom is a positively charged particle. He called it proton, and the electrons are actually revolving around the atom. So in the latest version, actually the electrons were moving in a cloud. So that is a part of the quantum mechanics. And later on, maybe we'll have a brief introduction about the quantum mechanics. All right, so according to Rutherford's atomic model, the nucleus is a tiny, densely packed compared with the atom as a whole. As a result, the atom is largely an empty space. So this is compared to the size of a football stadium, and the nucleus is just the size of a marble that is placed at the center of the stadium. So you can actually imagine how big is the space, how big is the empty space in an atom. Rutherford's model is seemingly incomplete because it needs to needs to be able to describe the chemical properties, and it wasn't able to answer why the electrons are staying in some orbit and it doesn't bump and hit the proton, because we all know that there is a electrical interaction, all right? So charge interaction between positive and negative charge. So the question now is, why does the electron does not bump the nucleus or the proton? So it goes to show that there is a need to revise and remodel the Rutherford planetary model, or add some key concepts to be able to explain the chemical properties of elements. So the next scientist that we're going to talk about is Niels Bohr. To understand where the scientists are coming from, we should be able to understand the predictions that are laid by, or are offered by classical mechanics about the atom. So since we have already know that Rutherford model is something like this, which is the nuclear atom, and we all know that we have a proton at the center and the electron is revolving around the nucleus. All right, so it predicts that the electron will actually lose, or eventually lose, energy, and we have some equations about that, and we're gonna show you that in the following slides. So let's continue our discussion about the atom by trying to understand the Bohr model of the hydrogen atom. So the hydrogen atom is said to have only one proton and only one electron, which is like this, and we know that the electron is revolving around the nucleus where the proton is located, and I can show you that using this animation. All right, so if you guys like contents like this, please click the subscribe button, hit the notification bell to get updated whenever I post videos like this. So guys, if you have any other comments, just leave it there and give us a thumbs up. You can also share this content to your classmates so that they can learn more about science. All right, so we mean to say that the since we knew that the electron is circling around our nucleus, it has its acceleration, and we know that there is also an interaction between the proton and the electron. We know that there is an electric force that is present in between them. So the acceleration is given by the centripetal acceleration is given by the A is equal to V squared all over R. And from Newton's law, we can relate this to the force Fc, and the force that powers the electron is equivalent to the electric force. So later on, we're gonna equate Fe and Fc. So we'll use Newton's law as I mentioned, where F is equivalent to ma, and finally we'll relate it to F is equivalent to k squared, Ke squared all over r squared, wherein this is the electrostatic force. So let's have that equation in the next slide. All right. So as I've said, Fe, or the electrostatic force, must be equal to the centripetal force. So given the two equation, we'll equate them to one another, and we're gonna have K, which is a constant, and later on I'm gonna show you the numbers that play in part of this constant. We have Q sub 1 and Q sub 2, which is actually the charge of the proton, which is positive E, and the charge of the electron, which is negative E. So technically they are the same, so we can just write this as E to the power of 2, or E squared. And since they have different sign, we write negative there. All right. So later on, the negative sign will play an important role in interpreting the results, all right, of the interaction. So we're gonna have K times Q sub 1 times Q sub 2 all over r squared, and is equal to Fc, which is equivalent to mass, times the velocity squared all over r. So we can actually remove one r by multiplying r both sides. All right, so we'll see here that r will cancel out, and another r will just remain out there. So from this equation, we can solve for the velocity, all right, of the electron. All right, so once we simplify, it's gonna be like this. So we can solve for the velocity right here, all right, by dividing both sides by m. So let's divide both sides by m. You'll see that it'll cancel out, and v is isolated here, but we're not done yet. So we'll have to take the square root, and I'm gonna show you that in the next slide. So we start from this, and we isolate v and take the square root of both sides. So this is the formula for the velocity of the electron. So we see that the velocity of the electron will greatly change with the radius. So because the mass of the electron is constant, the charges are constant, and 4 pi EO, or the vacuum permittivity, are constant. So the only thing that may vary here is the radius. So the velocity of different electrons are different with respect to their radius. So there's gonna be some discrepancy. All right, so you can use this to calculate the velocity of the hydrogen atom, or the electron of the hydrogen atom. So later on, we'll show how this formula works. Classical physics has failed to completely describe the atom. It seems that the formula that we have showed you earlier is compliant with Newton's law. But put in mind that Newton's law are not the only pillar of classical physics. We also have Maxwell's theory of electromagnetism. According to Maxwell, a charge traveling on a curved path will experience an acceleration, and hence it will continuously release electromagnetic waves. Thus, the electron is continuously losing its energy. So the Bohr model seems to be problematic after all, because according to classical physics, it predicts that the electron should spiral inward as it loses its energy. So as it loses its energy, it will release emission spectra, which is showed by this picture, and it cannot be predicted by classical physics. So therefore, there is a need for a new theory, which is put forward by Niels Bohr. The Bohr model has its solution and proof from the new emerging quantum theory. So according to Max Planck, some body emits radiation in an order of integral multiples and not in a continuous fashion. Hence, it is possible for the electron not to lose energy continuously. According to him, the energy emitted by the source is proportional to the Planck's constant, times the frequency of the source, and this is given by E is equivalent to NHF, wherein N are integral multiples and H is the Planck's constant and F is the frequency. And also this energy is related to the momentum according to Einstein by the formula P is equivalent to the momentum mv is equivalent to the energy all over c, which is the speed of light. So we can rewrite the formula as momentum p, which is equivalent to mass times velocity, is equivalent to the ratio of the energy to the speed of light, is equivalent to the Planck's constant times n times the frequency of the source all over c. So which can be related to the velocity of the source, in our case the velocity of the electron. We can relate frequency and velocity to the wavelength, so because of the wave theory. So we have momentum p is equivalent to mv is equivalent to the ratio of the energy to the speed of light, which c can be the velocity of our electron. So we'll substitute the corresponding formula for E, which is NHF based from Planck's assumption all over C, and this is equivalent to NH times F all over V. So we can actually derive for the wavelength using the formula for the wave equation, and we have momentum P equals mv is equivalent to NHF all over V is equivalent to N times the Planck's constant all over the wavelength. The wavelength here is actually the de Broglie wavelength. Alright, so de Broglie proposed that matter waves can exist. So the wavelength is the de Broglie wave, which is equivalent to the orbit of the electron. So if the orbit is circular, we have 2 pi r. So we're gonna substitute that in our formula. So the momentum P equals mv is equivalent to n times the Planck's constant divided by the wavelength. And since I've told you that this is just equal to the radius, we're gonna have n times the ratio of the Planck's constant divided by 2 pi r. Solution from the quantum theory. Bohr suggests that the angular momentum of the electron has to be constant. So he starts from the equation P equals or momentum P is equivalent to mv times n times h all over 2 pi r. So he relates the angular momentum L as the product or the cross product of radius vector r times momentum vector p, and it's gonna be mvr. So do not complicate thinking about it. He just cross multiply r to the other side. So he produced the quantity L, which is called the angular momentum. So we have mvr is equivalent to n times h all over 2 pi. And we know that these are just constants. So he have found out that the angular momentum L for the electron in the hydrogen atom is constant. So Bohr went on and tried to find the allowed radius. So here we're going to solve for the allowed radius for the hydrogen atom. Basically, the radius of the electron that is orbiting the hydrogen atom. So let's start with his formula. We have mvr is equivalent to nh. All right, so where n is the integer, n is equal to 1, 2, 3, 4, 5, and so on and so forth. So h here is the Planck's constant, and we have a constant 2 pi. So you will see that we can actually divide both sides by mv, and we're gonna find r, or we can divide both sides by mr, and we'll be able to find v. So let's divide both sides by mr, and we're gonna have velocity is equivalent to nh all over 2 pi times mass. All right, so we're going to substitute this formula in the results that we have had earlier from our relationship of the electrostatic force and the um, centripetal force felt by the electron. All right, so because this should be obeyed for the electron to move accordingly based on the predicted characteristic by the quantum and by the classical physics. So we'll use the formula that we have. We have Ke squared all over R is equivalent to mv squared. Now we're gonna substitute the velocity or the expression for the velocity in this one, and then try to square and then try to simplify. So we'll do that. So we substitute v is equivalent to nh all over 2 pi r times m to our equation. So we're gonna have Ke squared is equal to Ke squared all over r is equal to the mass times the quantity of nh 2 pi r times m raised to the power of 2. So we can actually simplify the expression first by distributing the squared. All right, so we're gonna do some simple algebra here, and it will result to 1 all over 4 pi times the vacuum permittivity of space times e squared all over r. So this is just k. So this constant right here is just k. So we just rewrite it in terms of some few constants. So E here is the basic charge, all right? So fundamental amount of charge or magnitude of charge, which is 1.6 times 10 to the negative 19 coulombs, all right? And square that, and here we have R. So once you simplify this, you're gonna have 1 all over 4 pi times vacuum permittivity times e squared all over r. So we have n squared, all right? So we square that times h squared all over 4 pi squared r squared times m squared. So what we can do right now is to cross multiply so that it will be easy. All right, so and yes, so cross multiply, and once we do that, it will result to 4 pi squared r squared times m squared all over 4 pi times the vacuum permittivity times m times e squared all over r, and this is equivalent to n squared h squared. So basically some terms will cancel out, like 4 pi and the mass, and we're gonna remove some here also, or cancel out some terms here, and it will result to m times pi r times e squared all over the permittivity. All right, so it's equivalent to n squared h squared. All right, so now you can solve for the radius by cross multiplying again. So we multiply that, and what we'll end up with this formula. All right, and r is actually it's equal to n squared h squared times the vacuum permittivity all over the mass times pi times the charge squared. So here, n is called the principal quantum number that tells us the size of the atom, or how far the electron shell from the nucleus of the atom. Bohr is partially correct. He must have believed that the electron is revolving around the nucleus in a circular orbit and have attempted to predict the precise location of the electron at all times. Hence, this is still in a classical point of view. The planetary model has worked for the hydrogen atom, but not for all the elements. The derivation in the last video is made from de Broglie's approach that matter can exhibit wave nature. Hence, we have verified that there is a wave and particle duality. This work has to come a decade later. Hence, Bohr doesn't know about this. This makes his work all the more remarkable. From de Broglie, we know that the electron could have a wave motion, and this is related to the momentum of the electron. We have the formula P, or the momentum P, is equivalent to mv, is equivalent to n, which is the principal quantum number, times h, which is the Planck's constant, divided by the wavelength. We can write this in terms of the wave number k, because this is related to the wavelength of the electron. So we will see that momentum P is equivalent to mv is equivalent to n, which is the principal quantum number, times h, which is the Planck's constant, times k, which is the wave number, all over 2 pi. So the premise of the uncertainty principle, this is where the uncertainty came from. Are we all aware of the wave number at all times? Basically, no. If we are not aware, we are also not certain about the momentum of the particle at a given time. That's true. And if we are not aware, we are also less certain about the energy of the particle at any given time. So we can write an expression in terms of the infinitesimal change in the wave number gives an uncertainty of the momentum of the particle. So we have the formula, or we are going to rewrite the formula for the momentum in terms of the wave number. We have the momentum P, or the change in momentum P, is equivalent to mv is equivalent to n, which is the principal quantum number, h, which is the Planck's constant, and delta k, that signify the change in the waves, or the number of waves, all over 2 pi. So from the equation, delta p equals mv is equivalent to nh delta k all over 2 pi. We have an expression for delta k, and that is equivalent to 2 pi r all over the lambda, or all over the wavelength. Now we are trying to look for the source where the changes in delta k, in the change in the wave number is coming from. And since 2 pi right here is just a constant, there's no other source but the change in the wavelength. Alright, so this change in the wavelength is actually the change along the x-axis. Alright, so therefore this is equal to the length traveled in the x-axis. So delta k depends on delta x. So we can write changes in delta k as seemingly equal to 1 all over delta x, because 2 pi r there is a constant. So we can actually get the product of delta k and delta x, so that we mean that they commutate, alright? Okay, so the degree that the quantity commutate as defined by probability is given by delta k times delta x is less than or equal to 1/2. Alright, so that's the a formula coming from the probability and statistics. So you can check if you want to And then we can write the new equation for this using the expression delta k, or the change in the wave number, times the change in the x position, all right, is equivalent to or less than or equal to 1/2. All right, so next is to show that delta k is equivalent to or less than or equal to 1 all over 2 delta x. Now we can plug this equation into the expression for the momentum that we have earlier, as delta p is equivalent to nh times delta k all over 2 pi times 1 is equivalent to nh all over 2 pi times 1 all over 2 pi delta x, because we know that 1 all over 2 delta x is just equivalent to delta k. And then we can simplify this as n times h all over 4 times delta x. And then what we need to do is to cross multiply to show that delta p, or the change in momentum, and change in the x-axis of the particle is equivalent to nh all over 4 pi, or equivalent to n times the h bar all over 2. So this formula can actually calculate the amount of uncertainty in the position and the momentum of the particle. So this is equivalent to a constant. If we let n is 1 for the hydrogen atom, we have the h bar all over 2. So that's gonna be h bar, all right, all over 2. All right. We will now write the energy-related uncertainty principle. So we remind of these questions and these premises, and we can use the expression E equals hf, which is this is given by Max Planck. All right, so E is the energy, and h is equivalent to the Planck's constant, and f is the frequency of the source. Actually, Einstein also used this in his formula for the photoelectric effect. And we have a formula for the frequency, which is f is equivalent to 1 all over t. And then the accuracy of measuring the energy released during an atomic process depends on the amount of time available for us to observe it. So basically, this is limited by this thing, or this variable over here, time. So if there is a change in time, and we can show that in the next expression, there will be a change in the amount of energy that we are gonna measure. So the uncertainty in the measurement of the energy has something to do, and is limited by the delta t. All right, so you just have to cross multiply delta E times delta t, and you'll see that that's equivalent to less than or equal to h. But there are more precise formulation of this, and this is related to the wave groups, and we can show that the uncertainty principle for energy and time is less than or equal to h all over 4 pi. So this is due to the limit, okay, of measuring capability, and since there are errors, so we have to correct ourselves within a certain limit of uncertainty. All right.